You ready to look at hydrogen bonds? Now, if you're in biology, physiology, things like that, you probably already learned about hydrogen bonds. We're just going to look at it from a chemical point of view, right? On, not really the applications of it, in protein shapes and why DNA has its shape it has, adenine and guanine, all that kind of stuff. Not my stuff. We'll look at it on why hydrogen bonds are so much stronger than you would anticipate because they really are just dipole-dipole forces. They're just like super dipole-dipole forces. Well, let's talk about why that is. Okay? And it's not really a bond. The hydrogen bond is a misleading word, all right? Because it's not really a bond per se, right? It's not like a covalent bond, like an intramolecular bond. It's an intermolecular force. It's just super strong. We just call it a hydrogen bond, right? But it's not nearly as strong as a covalent bond. So again, special case of dipole-dipole forces. And remember, there's four things we talked about that really determine the strength of the intermolecular forces, right? How polar is the molecule, if it's polar? How big is it, the size? We looked at how close they can get, the distance. The closer you can get, the stronger they're going to be. And then temperature. So let's take temperature out of it. Temperature just tends to disrupt. The hotter it is, the more thermal energy, the more it disrupts the intermolecular forces, right? Makes them harder for them to lock into place. So we're going to be assuming constant temperature here. So let's look at these factors. Now, because of the two reasonings I'm going to have here, these are stronger than your typical dipole-dipole forces, which was in, probably less than 10-ish range. Okay, so a really strong dipole-dipole force, traditional, would kind of fall in the lower range of this. So even the weakest species that can hydrogen bond are going to be stronger than most of the strongest dipole-dipole, traditional dipole-dipole forces. So you're talking 10 to 40 kilojoules per mole, not up in the 3, 4, 500 kilojoules per mole for like covalent bonds and whatnot. But still pretty surprising, especially for how small these molecules are. So what causes this? Well, factor number one, polarity. So if you're looking at polarity, we're talking about the most polar species we can get, super strong dipole moments, all right? So we're looking at the highest electronegative atoms. So if we look on here, that's going to be these babies up here. So the fluorine, right, oxygen, nitrogen. Chlorine comes close, right? So in some scenarios, chlorine might or might not. So we're going to make it easy and just say, doesn't make the cutoff. It's going to be fluorine, oxygen, and nitrogen. You see those highly electronegative atoms, things like water, HF, ammonia, small alcohol, CH3, methanol, ethanol, those kinds of things. They have this ability to hydrogen bond. But it's more than just being really polar. It also has to have very close approach, right? If we have really polar molecules, but they can't get real close, right? You might have dipole-dipole forces, but you're not going to have hydrogen bonding. And so why it's named the way it is because of the next, right, factor. Those highly electronegative atoms, fluorine, oxygen, and nitrogen, must be bonded to a hydrogen atom. Thus the hydrogen bond. So why does it have to be hydrogen? Hydrogens are tiny. They're the smallest atoms. They're just a proton, right? So if I have two molecules, so say this is ammonia, NH3. These hydrogens are really teeny, so this doesn't do it justice, right? But you get this really, really polar species because those large delta EN, so the hydrogens have this partial positive, partial negative on the nitrogen. Well, same thing's true with another ammonia that comes by. So here's this really highly polar molecule. But that hydrogen makes for a really close approach. And so they can get super duper close, right? And the closer you get, the stronger those intermolecular forces are going to be. And so the hydrogen forms like a bridge between the two nitrogens. So it's covalently bonded to this nitrogen, this ammonia. And then hydrogen bonds, so you got this lone pair here on the nitrogen. Big negative region here, super highly polar bonds. This partial positive hydrogen is very electrostatically attracted to it, and it gets really close. And that twofer there gives you really strong energies. So again, it is a dipole-dipole force, but we don't call it a dipole-dipole force because of the extreme energetics of it. We call it a hydrogen bond, right? And so you get kind of that 180-degree bond angle. So it's like the hydrogen bridges. And the hydrogen bond is longer than the covalent bond, right? It's weaker. So you get something that kind of looks like that. And then that can spread off in 3 dimensions, right? So these species tend to liquefy way sooner than you would anticipate. right? You're like going, so like water, we wouldn't expect it to have the boiling point that it has because it's so tiny. It's not real big. So we would expect it to have, a certain kind of, as size increases, things are more polarizable. And we can look at polarities and look at trends, and things follow pretty good trends, but there's certain molecules that have hydrogen bonding ability. They don't follow the trends, right? You'd be like, hey, everything's moving great, dun, 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 and then all of a sudden, boink, something's way off. You're like, what happened? It's because things like ammonia, HF, and water can hydrogen bond and have massively stronger intermolecular forces, way higher melting points and boiling points, and molar heats of vaporization than you would anticipate. And that's why water is such a great coolant, because it takes a tremendous amount of energy to break these hydrogen bonds. So this is going to be a little easier to see. I showed the molecules, but let's draw it on the board and show you where this hydrogen bonding comes into play. You got it? So it has to be fluorine, oxygen, or nitrogen bonded to a hydrogen, which then comes close to another fluorine, oxygen, or nitrogen, a lone pair on one of those, and forms a bridge. The hydrogen forms like a bridge between those. And it could be a fluorine, hydrogen, oxygen, hydrogen, oxygen, doesn't matter. Let's take a look at it. All right, let's take a look at the case of the ammonia. We could have picked any, water. Water's the typical one. You could read that in a book anywhere. So let's take ammonia, right, which is that trigonal pyramid. Okay, so that nitrogen's got the lone pair, it's got the 3 hydrogens in a trigonal pyramid arrangement. So I just kind of drew it like a traditional trigonal pyramid. But what happens when you bring another ammonia? How does it rotate around and form this hydrogen bond, right? Well, obviously you've got this incredibly large delta En, right? So again, nitrogen, fluorine, or oxygen with hydrogen, high delta En, very polar bond, asymmetric, superpolar molecule, right? So that nitrogen's pulling electrons away from these hydrogens. And so that is effectively a proton, right? You're getting a really big positive. It's not an ion, but you got a pretty strong partial positive and a pretty strong partial negative. So if I bring another ammonia up, that lone pair on that nitrogen right here, see, that's going to be very attracted to these hydrogens. So if we bring another ammonia up, it's going to rotate itself so that the nitrogen atom, let's distort this. And we're going to get this partial negative here on that nitrogen, and you got the partial positives here. But can you see right here, we'll draw the dashed line for the intermolecular force and the solid line for the intramolecular bond, right? And again, you're talking 10 to 40 kilojoules per mole there. You're talking, 150, 200. I haven't memorized the nitrogen-hydrogen bond energy, but a single bond probably 150 to 200 kilojoules per mole. Double, triple bonds probably higher than that. Ionic bonds even higher than that, right? But can you see what I see? This is your typical way of recognizing hydrogen bonding. I mean, it's really easy. You just look at the Lewis structure. If you draw the Lewis structure and you see hydrogen bonded to nitrogen, oxygen, or fluorine, bam, it's got hydrogen bonding. Really easy to locate just from a Lewis structure. But you can see this kind of 180-degree bond angle forming that bridge between the nitrogen covalently bonded to the hydrogen, and then that intermolecular force there. That's your hydrogen bond to that lone pair on that nitrogen. That is your intermolecular force. That's your H bond. So we call it an H bond, right? Bond, H bond. Very large delta En, right? So requirement number 1, that superpolar situation. And then it's got to be attracted to a lone pair on another highly electronegative atom, right? So let's talk about that hydrogen right there. So that hydrogen is attracted to the lone pair on a nitrogen, oxygen, or fluorine atom. Again, which is highly electronegative. So that satisfies requirement number 1. You've got that really, really strong polarity going on. And requirement number 2, that hydrogen is really, really tiny. So these nitrogens can get really close to each other, right? And so because of the hydrogen, allows very close approach. Therein is the essence of hydrogen bonding. And you could put a water molecule here with a water molecule. You have the OHO. If it was HF, you'd have the FHF, right? Whatever can do that. And it can be between two different species or the same species, doesn't matter. And that tends to create really, really way higher boiling points and melting points, molar heats of vaporization, all these basic properties, way different than you would anticipate just on the size alone, right? Because remember, the bigger something is, the stronger the intermolecular forces. We're going to hit that pretty hard in the next video on London dispersion forces, but it just has more polarizable electron cloud, right? More electrons, more easy to distort it, okay? So the small ones tend to have lower melting points and boiling points than molecules with bigger ones. So if I put a phosphorus there, right, or something, if you look on the periodic table, do I have a periodic table? So we would find traditionally as you move down, like NH3, PH3, they're getting bigger and bigger and bigger. So they tend to get stronger in molecular forces, so that the boiling points tend to increase as you go down the periodic table with those trends. But not true. You would think the one that would have the lowest one, the smallest one with the nitrogen, has the highest boiling point in that series. It's true for all the columns. They're like, what's going on, right? It's because they can hydrogen bond. Boop. Really close. All right. So I'm debating whether I want to talk about the effects on biology. I'm not going to write them down. There's some really cool stuff, but this is chemistry, not biology, right? But if you take biology or nursing chemistry, things like that, one thing you're going to talk about is proteins, which is interesting because you get these really long molecules, right? Just, and then they're rotating and stuff, and they can actually kind of curl back around, and you can get this intramolecular hydrogen bonding going on. It's kind of weird because it's like a snake eating its tail as it comes around. Say you've got a nitrogen-hydrogen bond right here, right? And this protein rotates around. Maybe there's another fluorine or an oxygen here with a lone pair. Boop! You can form this hydrogen bond between one end of a long molecule and the other, and it locks this band or loop into place. So you can get these with proteins, where there's these huge molecules. You can get these really cool, beta pleated sheets and alpha helices, all these cool little shapes and curves that are locked into place with hydrogen bonds. Of course, if you heat it up or something or whatever, you can disrupt those. So you got to watch out for that. I forget that what's called denaturization or something, denaturation. Not a biologist. And same thing with DNAs. I forget which base pairs lock in with each other, but it's like they're perfectly made for each other. And you get this double or triple hydrogen bonding, right? So you get some of these bases in DNA that you get that helix structure, and these bases lock in. There's some of them where you get these two places that lock in hydrogen bond. There's another one that locks in with three, right? It's just like these perfect puzzle pieces that fit together, just designed beautifully. And same thing's true with molecules. You can get something that has like double hydrogen bonding ability, for example. And this will affect some properties later. We'll do a whole nother video when we look at liquid properties. But let's say we do, something like CH3OH, which is methanol, right? So if we draw the carbon, can you see the hydrogen bonding ability there? So on an exam or quiz, if I give you a list of, say, 5 molecules and say which ones can hydrogen bond, you can just look at it. I mean, you probably don't even need the Lewis structure. You can go, there's a hydrogen bonded to an oxygen. Boom, it can hydrogen bond to itself or with other species, right? You can see that. So you get the oxygen here of another one. You see the OHO. But now, what if we do an alcohol that has 2 OHs? It's called a diol or something like that. You can get triols and things. So let's take a molecule now. Let's say we got this. You ready? Let's do an OH there. And let's do an OH there. Right? So we got 2 carbons. with two OHs. Now we have two locations that can hydrogen bond. So if you're comparing this one to this one and go, which would have the higher boiling point, you would have to pick this one because not only is it bigger, it's got multiple hydrogen bonding possibilities, right? So I'm going to put higher intermolecular forces there, but that would have the higher boiling point. We talk about the viscosity later, which is the resistance to flow. So if you have lots of OH groups, it tends to be like if it's a liquid, it doesn't flow as easily, right? So it gets kind of thicker, gooier. We use when we do glass blowing and we got to insert glass tubing into rubber stoppers and stuff, we lubricate the holes in the rubber stoppers with glycerol, which is 3 carbons, each with an OH group on it. And that stuff's gooey, man. It just kind of oozes and it gets on your fingers and you're like, this is gross, right? It's because it's got that triple hydrogen bonding ability, which, right, increases its boiling point, increases its viscosity, all these cool things. There's so much neat stuff with hydrogen bonding. I'll let you in biology and biochemistry to look at the cool applications of it. I just want to look at the chemistry of it. All right, guys.